Hi, everyone. This is Jason Key at Harvard Medical School, SP Grid. Thanks for signing on. Today, we have Toshio Moriya joining us from MPI in Dortmund. Before we get started with that, a couple announcements. Next month is EMAN 2, Stephen Lutke. We're keeping on the Cryo-EM theme. Then we shift over to NMR for a while for our back-to-back talks from Frank Delaglio. Then Simple in January, and then to some computational chemistry for ORCA in February. So if there's titles you want to hear about, if there's developers you want to hear from, email us, let us know. We would like to hear it. So with that, Toshio, are you there?
Yep, I am here.
All right, go right ahead.
Hi, thank you very much, Jason. So, hello everybody. System checks?
Yep, looks good. Go right ahead.
Good, all right. So, thank you for the kind instruction, Jason. I'd like to express my gratitude to the member of SP Grid, especially Michelle and Jason, for inviting me and organizing this webinar. Before starting my presentation of the Sphire, I would like to congratulate the 3 scientists who led us to the success of 3D Cryo-EM field for receiving the Nobel Prize in Chemistry this year. Okay, let's start. Today, I'd like to talk about our software package for single particle analysis, or SPA. We named it Sphire. Sphire is React version of Sparks. For this project, we set up 4 goals. First, introducing the easy-to-use graphical user interface, or GUI, for the people new to the single particle analysis and Sphire. Next, we simplify the SPA pipeline by automating the major steps, such as 3D refinement and 2D clustering. To keep our package comprehensive, we also added new algorithms to catch up the technological advancements of our field, including the support for water phase plate datasets. We also expanded the concept of validation by reproducibility to other major steps. This approach was originally developed for Isaac 2D clustering, which is one of the most successful algorithms in our package. As a start, we simplify the SPA pipeline. Now, there are project settings and only 7 major pipeline steps. We also introduce the pictograms for all the major steps so that they are easy to remember and recognize the purposes. The first step is project settings, then theta for CTF estimation and assessment, window for particle picking and extraction, Isaac for 2D clustering, Viper for initial 3D modeling, Meridian for 3D refinement, and B-factor sharpening. So the 3D for 3D variability estimation and 3D clustering. And finally, local res for local resolution and 3D local filtering. Since we assume micrograph movie alignment is done on fly during the microscopy session, we consider movie step optional in our pipeline. In addition, the utilities block provide easy access to all the utility commands. To make the organization of the Sphire pipeline explicit and the interface user-friendly, we developed the Sphire GUI application. In the left area of the main window, the pipeline steps are displayed as pictogram icon buttons, and they are arranged in order of the execution. Clicking one of the icons will display a list of the commands in the middle area. These commands are associated with selective step, and they are categorized into 3 types. The ones in the commands are in the mainstream of the pipeline. In most of the typical projects, you just need to run these commands one by one from the top to the bottom. The ones in the alternatives are, the one in the alternatives are for alternative pipelines. For example, PDB file conversion is for jump-starting 3D refinement from PDB atomic model. Please note that only some steps have alternatives. The ones in the utilities are utility commands associated to the selected pipeline step. They facilitate execution of a project and often provide links between main steps. You can also find all of these utility commands under Utilities block. Selecting a command button displays the associated command page. The page provides an interface for the option setting of the selected command. The options were divided into main and advanced tabs here. For most of the project, you need to set only main options and leave the advanced options to default settings. For input file and input directory settings, you can use buttons on the right side here. The buttons on the left side are for restoring the default values or project settings. These. The project settings are indicated by green. This example shows point group symmetry here. I will explain more about the project setting in the next slide. Finally, left bottom area is settings for MPI, messaging passing interface, and the job scheduler available on your system. You can save the option settings as a text file and restore it later. When you are done with all settings, pushing Generate Command Line button displays the command line. Finally, use Run Command button to start the execution. To start a new project, we recommend to register the project settings using this page. Here, you can set the project-dependent constant values, such as pixel size and point group symmetry. These parameters are used in many pipeline commands. Registered values are set as a default value of corresponding options in each command page of the GUI. They are indicated by green text as shown in the previous slide. This eliminates the necessity of retyping same values over and over again. However, you can still run each command from the GUI without registering the project settings using this page. The first step of the Sphire pipeline is CTF estimation and assessment. Using the CTF assessment tool, you can visualize the global statistics of the estimated CTF parameters and related diagnosis data produced by Tyra. Then it is easy to set the thresholds of the outputs and do the micrograph screening. The figure shows the main control window, which you mainly interact with. This window is a histogram of a selected parameter showing the global trend. This example shows defocus. Defocus value of that is defocus values of all micrographs. You can set the thresholds by moving blue line and red lines with mouse. Green line indicates the value of selected micrograph from this list. You can also change the histogram to another parameter, such as astigmatism amplitude, through the main control window. Also, you can inspect the quality of CTF model fitting visually with this plot. Vertical lines indicate three types of the flexing limits computed by theta. Finally, you can apply all threshold settings and save the section result. The next step is Isaac 2D clustering and beautifier. It is Isaac where we first introduced the concept of validation by reproducibility. The idea of this approach is simple. If we learn 2D clustering multiple times, each particle should be always assigned to the same the same class, and should result in the same 2D alignment. Isaac is also capable of handling data set with strong preferred orientation. As an example demonstrates, the algorithm can handle protein with a long shape instead of globular shape, separating particles into many classes and centering them well. Because of the recent optimization, Isaac now finishes within hours instead of days, and can handle larger dataset than previous version. However, in a typical project, Isaac also shrinks particle images to speed up the process. Please use the beautifier to obtain the high-resolution version of Isaac class averages by defining 2D alignments of each class using the original image size and full CTF correction. This is another extreme example of a long-shaped particle. As you can see, Isaac can classify even the views, all showing similar rod-like shapes. Other 2D clustering programs have difficulty with this kind of dataset. Because of this, many people use Isaac, especially for particle screening. We believe Isaac is one of the most successful algorithms in Sparks. Therefore, we apply the concept developed for Isaac to other SPA measure steps, especially validation by reproducibility. The ab initio 3D reconstruction of Sphire is reproducible Viper or R-Viper. With this, we added validation by reproducibility and automatic outlier detection. On top of the basic algorithm we call Viper. Each figure shows the result at the right, and the input Isaac class averages at the left. Remarkably, a Viper can achieve a resolution higher than 70 angstrom by itself when the quality of the dataset is good. To simplify the pipeline, we newly developed maximum likelihood-based 3D refinement and automated this major step of SPA. Like the other statistical methods, median has an intelligent state control, uses winner reconstruction with full CTF correction, and marginalized 3D alignment parameters for angular smearing. By tracking the resolution change, the intelligent state control automatically decides the best parameter settings for each iteration, such as image size and refinement algorithm. Recently, we introduced a polar coordinates representation of reprojection and particle images for the 3D alignment stage of each iteration. This resulted in a significant speedup. Now, median finishes within hours instead of days. It is also able to handle larger data sets. I believe one of the most distinct features of Sphire is combination of the 3D variability assessment and the focused 3D clustering. Notably, the 3D variability can directly reveal variable regions, which are invisible in density map. On the other hand, local resolution cannot visualize all of the variable regions because it considers not only noise, but also signal. Here, the noise includes the variation or movement of the density at each voxel. In Sapphire, you can use the 3D variability map as a 3D focus path for the clustering. This focused 3D clustering is implemented in Salt 3D. The automatic outlier detection and validation by reproducibility are also added to the Salt 3D as a new features. Each sorted group can be further refined by subset refinement. Moriya provides this function. The final step of the Sapphire pipeline is local lens. It consists of local resolution estimation and 3D local filtering. Importantly, the local resolution of Sapphire is based on FFC. Therefore, it is directly comparable to the global resolution computed by the standard FSC method. Our local filtering is based on this local resolution. It produces a more accurate visual representation of the map. That means no over-filtered regions, no under-filtered regions. Additionally, the Sapphire supports micrograph movie processing as an optional step. For micrograph movie alignment, the GUI provides a front end to launch external application, Umbrella and SunMovie. Both were developed by Dr. Grigory Flor. Similar to the CTF assessment, we also developed a GUI tool for drift assessment. With this tool, you can visually check the statistic of estimated drifts. Again, it helps you to screen micrographs. The slide shows the main control window, which you mainly interact with. The overall drift histogram will let you set the threshold by interactively moving blue and red line with mouse track. In the top right of the main control, you can display and use many other plots, such as the drift per frame. Also, you can visually check the drift trace of each micrograph. Finally, you can apply all threshold settings and save the section as a result of micrograph screening based on the drift. The last block in GUI is utilities. It brings together various utility commands that facilitate execution of a project and often provide links between main steps. All commands under utilities category in all the pipeline step blocks can be found here. As the system matures, we expect the number of these utility commands will increase. To evaluate the performance of Sapphire pipeline, we reconstructed many proteins using Empire datasets as well as in-house datasets. We try to cover different molecular size, point group symmetries, and shape as much as possible. Here is a result from Empire datasets with T20S proteasome. We achieved 2.89 angstrom, which is comparable to the original published work. We are also continuously trying to improve the resolution of our standard dataset. This is TCDA1 biotoxin protein. With this, we achieve 2.87 angstrom. Finally, We are currently evaluating the performance of the Sphire faceplate support with several datasets. This is a felting dataset obtained with water faceplate Cryo-EM. We gained the 2.87 angstrom structure. Remarkably, it took less than 70 hours on our cluster using 192 CPUs. Furthermore, we support easy visualization of Furthermore, we support the easy visualization of the water phase shift development with CTF assessment tool. These results prove that our Sphire pipeline is capable of near atomic reconstruction for typical SPA projects. Today, I presented only the overview of the Sphire user-friendly pipeline and its easy-to-use GUI application. If my presentation made you interested in the Sphire and want to learn how to execute the Sphire pipeline in detail, please try out the step-by-step Sphire tutorial with the sample dataset. We are also organizing the International Sphire workshop periodically. Before closing my presentation, I would like to acknowledge the Sphire project members. Stefan is the leader of the project and organized the collaboration with Paul. Paul is the lead developer of the Spark system and developing the core algorithms for Sphire pipeline. Christos is the main designer of the Sphire pipeline and evaluating the implementation. Marcus, Torsten, Zong, and me are software developers, implementing the core algorithms and GUIs. Philippe takes responsibility of wiki page and evaluation of the Sphire pipeline. And this is the last message from all the Sphire project members. This concludes my presentation of our Sphire software package for single particle Cryo-EM. Again, thank you for joining and your attention.
So,
okay.
The mic is ready. Anyone who has questions, you can send them to the group chat. You can send them here. The chat window is here, and I can pass them on. We also have a group here. If anyone here has questions, you can raise your hand. You can come up to the laptop, and we can pass this on. I had a couple just technical questions. I know that you have a sort of framework in Sphire that can support schedulers for HPC resources. I'm curious which schedulers you currently support and recommend.
Our cluster is using the SGE, some of the grid engine.
Yep.
And so also so SGE is one that we have most experience with. And some people use PBS and Pathway. Toki, I can't pronounce well, but our user uses many different systems and seems to be working all right for most of the system. So if it's general enough, usually it should work. But I recently got the mail from the user suggesting that maybe we want to have more variable that we can use for the creating the job submission script. So here, I think, can you see the screenshot still?
Yep.
Yeah, here so the person is saying that there might be he suggested adding a little more parameter so that the software will have the flexibility to handle more complex setting of the job submission script.
Yeah, I think that the job submission is is sort of tricky business because they can be customized for individual clusters, individual sites. So yeah, it's one of those not easy to satisfy everyone sort of things. I do think that Slurm is gaining traction and is.
That's right. Slurm is also by default it's supported. Sorry,
okay, good. Yeah. So with that one, I think you're going to cover a lot of sites. So that would be a good way to go.
Yeah, sorry that I forgot to mention it. Yeah. Yeah.
Great. Where do you recommend people go for documentation and help? And are there tutorials or test data sets people can download?
Right. I think that you kindly send me the announcement page of SP Grid. Can you see it?
Yep,
So
that's the one.
here, the homepage is the best place to start with, right? Here. And if you do the documentation, then I'm sorry, this is editor mode. So, okay, you see like this. So it's like the GUI. If you push it, then you will see all the help contents of the each command, for example, right? So like this. So it's like a GUI, but for help. And also that the download install is organized like this. If you push it, it'll come up the page of the latest of stable release. And so this page contains an installer, tutorial, and a dataset. So this tutorial and dataset is a very the good place to start run the Sapphire and check it. So this is how where I recommend to the see first.
Great. All right. Any other questions? All right. Well, with that, we'll wrap it up. Toshio, thank you very much.
Oh wow! Thank you very much. Yeah, thank you very much again, and I really had enjoyed this talk.
Right. And thank you everyone else for joining. Take care.
All right, take care. Bye.
Bye.